Hey everybody, Morgan here. So we're going to be looking at the last few pages of the lecture outline dealing with the periodic table today. And to understand what we're talking about, we need to discuss for a few minutes a concept from physics called Coulomb's law. Now, it is the law of attraction for charged particles. And it says that the force of attraction, or the Coulombic force, equals a constant, K, we don't care what that is, times the magnitude of the two charges, divided by the distance between the charges squared. Now this is what we call an inverse square law, because the relationship between the force and distance is an inverse, and because it is squared. So what this means is, if you have 2 times the charge, if the charge doubles, you have 2 times the attraction. But if you have 2 times the distance, you get 1/4 of the attraction, because it's 1/2 squared. Okay? Now that's going to become really important, because in our current model of the atom, we have a nucleus, which is the home of all the positive charge. Then we have the orbitals, which is the home of all the negative charge. And Q1 is basically the amount of positive charge, and Q2 is the amount of negative charge. And then the distance between the positive charge and the orbitals is the distance that we're talking about here. Now, often this positive charge is referred to as the nuclear charge. Okay, so now what does this mean for attractive forces between the nucleus, which is the protons, and electrons? The protons pull in the electrons. So the farther away they are away from the nucleus, so we picture these rings that we've talked about, the farther away they are, the less attractive force there's going to be. And it's easier to remove them because they're not bound as tightly. But the greater number of electrons and protons that you have, the greater the attraction. And that pulls them in even tighter and holds on to them tighter. Now this changes a bit when you have an ion. So let's imagine that we've got, positive charge in here, a full shell of electrons, and then another shell that only has, say, 1 electron. When that 1 electron leaves to form a positive ion, you always lose the outermost electron. So when you lose that electron, the remaining electrons are closer to the nucleus, because you've lost the only one that's in this outermost shell. All the other electrons are closer, and they're going to be held on to more tightly. It's the opposite when you have a negative ion, because you're adding electrons out here, and you're adding them a pretty good distance away from the nucleus. Now what this allows us to talk about are the 4 periodic properties: ionization energy, electron affinity, doesn't matter what order we list them in, atomic radii, and electronegativity. Those are the 4. So let's go on and let's look at those now and talk about each one of them. Okay, so atomic radii. This is a measure of the size of an atom. Now it's based on the idea of, a circle halfway across is the radii, except this time it is a sphere instead of a flat circle. It's 3-dimensional. And Coulomb's law is going to govern all of this. So what happens is as we go down, the outermost electrons are farther away from the nucleus. And Coulomb's law says they are less attracted. And because they're less attracted, that means the atoms grow in size. Okay? Now, the exact size is a fuzzy thing because this is kind of like looking at a cloud. A cloud does not have a well-defined edge. And the size of these atoms is really dictated by electron clouds. So these are approximations. They're good approximations, but they're approximations. So the real reason they're getting bigger as we go down is because the outermost electrons are farther away from the nucleus, and Coulomb's law says less attraction. Now, atomic radius decreases from left to right within a given family. And that's because the electrons are going into the same energy level or the same orbitals, but you're adding more protons than electrons. So in Coulomb's law, you are increasing the charge, but you are not increasing the distance that they are apart from the positive charge. Okay? Now, typically for ions, if you have a cation, which is positive, it's smaller, and an anion is larger than their respective neutral atoms. Cation lost electrons, so you have more protons than electrons, can pull them in tighter, and the electrons that they're pulling in are closer. Opposite for an anion, an extra electron can't pull it in as tightly, and it's been added a very good distance away from the nucleus. Okay, so that's the whole bit there about atomic radii. I'm going to move on to the next page now, talk briefly about electronegativity, although it comes up much more in our next chapter. So electronegativity we can call the tendency of an atom to attract electrons towards itself. Okay. Again, we're talking about the same thing here. It's the attraction. It's Coulomb's law. So it increases as you go to the right because you're adding more protons than electrons. So Coulomb's law says goes up. You're increasing as you go up towards fluorine, which has the highest electronegativity, because fluorine's very small. So if the protons and electrons are close together, that's a stronger attractive force. Now, you don't have to memorize these. We're always going to tell you these numbers. You should know that fluorine is the greatest and cesium and francium the least, so it increases as you go that way. You'll notice we don't list any for the noble gases. See, these are measured in compounds, and the noble gases don't form any compounds. And we haven't listed a whole lot of the lanthanides and actinides because, well, there aren't a whole lot of compounds down there either to talk about. Okay. Now, next we're going to go on to ionization energy. And ionization energy is probably the most important one of these for this chapter. It's the energy necessary to remove an electron from an atom in the gas state. Now we always remove the outermost electron, the last one there, the one that's farthest away. Okay? Now, it's a little bit uneven. Kind of looks like an EKG. You will notice that the highest ionization energies are always for noble gases, and that the lowest ionization energies are always for alkali metals. That's because with the alkali metal, you've just put an electron in an orbit that is farther away than the others from the atom. And for these, you have completely full shells, which means a high Q1 and Q2 in, Coulomb's law. But the d, the distance downstairs in Coulomb's law, has not been changing. Alrighty. Now, the last one is called Electron Affinity. And it is kind of the opposite of Coulomb's law. We say the energy change associated with the addition of an electron to a neutral atom. Goes from high to low. You'll see a graph of it down here. Beryllium and magnesium have very high electron affinities. Okay. Fluorine and chlorine, very low. It's quite easy to put electrons onto fluorine and chlorine, so it releases a lot of energy because they become very stable in the process. Okay. Almost all of them are negative. There's a few group 2s that are positive, group 1s occasionally, and noble gases occasionally also. Okay, so that's a brief tour of your periodic properties. Okay, if you get interested in it, want to explore it some more, there are several very good videos available on Khan Academy. Okay, thanks for tuning in. This is Morgan, signing off.